Hello, and welcome to today's session on understanding time estimation. Time estimation is a very important phenomenon because it's pervasive in our everyday lives. If you're driving down the road and you're approaching a traffic light, you might see from the distance that it's green, and you might begin estimating how much time you think you have before that green light turns to yellow and then to red also. If you're in conversation with a friend or a family member, typically it's polite to wait for that person to finish, wait for some interval, an estimate of the time that's elapsed since they've finished, and then for you to proceed thereafter. That is, before we interrupt them, we want to make sure that we've given them ample time to complete their thought. So we do time estimation all the time. In fact, lots of animals have demonstrated their capacity for time estimation, and certainly humans do this all day, every day. So it's something that is so frequent that we might take it for granted. We're a little bit like the fish that doesn't know the water is wet. Today we're going to try to understand how it is that time estimation might be possible. We'll think of some of the different ways of measuring time estimation. And we'll also think about maybe some of the physiology that underlies time estimation. Okay, so let's get right into it. We can talk about the comparison between physical time, which we're going to put on an x-axis or an abscissa, and psychological time, which we're going to put on our y-axis. So we can think of real time as being measured by a watch or a stopwatch. Maybe the watch that you have on your wrist would be a fair indicator of real time. We might call that time out there in the environment. Okay? And maybe that watch is ticking at something like 1 tick per second. We can contrast that with what we might call psychological time. And as I said a moment ago, we would plot psychological time on the y-axis, or the ordinate, and on the abscissa or the x-axis we might plot the physical time that we have from our stopwatch, or the watch that we have on our wrist. And then we have a measurement of our psychological response to that physical time. We might call this a psychophysical function. Remember that psychophysics is a branch of psychology that's involved with finding quantitative relations between physical stimulation and psychological events. So we have a psychophysical function. Psychophysics is what we're going to be talking about today, in addition to some pharmacology and so forth. To set the stage a little bit, it will help us to have some vocabulary that we'll be using certainly in this section, but also in other sections throughout our course. So one idea is the idea of veridical perception. Now that might be a new word to many of you. Veridical perception sounds like, if you listen not so closely, it sounds like the word vertical. It's not vertical, it's veridical. 4 syllables, not 3. And we can talk about veridical perception as being truthful perception, one that corresponds to some kind of known standard. In the case of time estimation, we might think about having subjective estimates of time, our perception of time, that correspond to the physical standard that we might get, again, from the watch on our wrist. Okay? So this is indexed by a physical measurement, maybe by a stopwatch in the case of time perception. But if we think about the perception of other kinds of phenomena, we might be using a light meter or a sound meter, whatever the case might be, to get some kind of physical measurement. And we can ask, to what extent is our perceptual experience corresponding with that known physical standard? To the extent that it is, we might call that veridical perception. And as we'll see today, there are many times in which we're not perceiving veridically when we talk about time estimation. We can also contrast two commonly used terms that we, in everyday life, typically use somewhat interchangeably, but in the scientific realm, we need to distinguish. One of these terms is accuracy, and one is precision. So we might define accuracy as the extent to which an observation matches a standard. For example, to what extent does your estimate of time match that which we have from our stopwatch? We can think of precision as the fineness or smallness of a measure. And this is sometimes expressed in the number of digits of precision. So we can measure time, for example, down to milliseconds, which would be 1,000th of a second. That's 1 times 10 to the negative 3rd. We can measure it in microseconds, 1 times 10 to the negative 6th. That would be 1/1,000,000th of a second. We can measure it in nanoseconds, 1/1,000,000,000th of a second, 1 times 10 to the negative 9. Or we can go in the opposite direction. We can talk about seconds or hours or days or weeks, months, years, centuries, millennia, and so forth. So lots of different scales of time, and we can talk about the different levels of precision that we have. One more example on the distinction between accuracy and precision with respect to timing. This might help make the distinction. We can think of having some kind of clock, perhaps an atomic clock, that we have agreed carries the correct time. And then we can all synchronize our watches to that. Maybe we synchronize the watch to 4 o'clock to be in accordance with that atomic clock. Now you might imagine that some people, for whatever reason, synchronize their clock a little bit inaccurately. Maybe some people set their watch 1 minute fast, others set their watch 1 minute slow, and so forth. We have then an inaccuracy. We have some kind of departure from what the current observation is versus some kind of known standard. Separate and apart from that mismatch that we might have relative to that standard, which would be an example of an inaccuracy, we can talk about the fineness of that temporal measurement. Temporal is time-based, so we can talk about measuring that time down to the second or down to the millisecond. A millisecond would be a more precise unit of measure than what a second, and so forth. So these are, in everyday life, similar concepts, but they're distinguishable here. Finally, we'll talk about this notion of a representation. Another word that we frequently use in everyday life. It has a relatively precise meaning in the world of memory research. And later on in today's session, we'll see that memory plays an important role in time estimation. Here, we can give a definition of representation as a correspondence between two systems such that the state of one system provides information about the other system. And as you might remember from Introduction to Psychology, there are different kinds of representations. One variety is analogical, another is symbolic, and as I mentioned, these are often used in memory research. Just to refresh your memory about different kinds of representations, let's talk a little bit about a symbolic representation. A symbolic representation is one in which there is an arbitrary relationship between the state of one system and the state of another. A very simple example of that would be our own speech system and the way that we represent it using letters. So up here, you can see that we have a V, the first letter in the word vocabulary, and we, by social agreement, have come to the agreement that we have this kind of a shape corresponding to the V or V sound, as in vocabulary. Okay? So when we see this, this corresponds to V, the V sound. But it didn't have to be that way. We could have lived in a different society where we had perhaps a circular symbol that corresponded to the V sound. Somewhat arbitrarily, but by agreement, we have decided that this V corresponds to the V sound. And that would be an example of a symbolic representation because the association between those two, the V sound and the letter V, is arbitrary. Another example would be the word 3 and the numerosity. Okay? I clicked 3 times, and I have this sound that we call the word 3, and those two go together. It could be the case, though, that we could represent the numerosity 3 analogically rather than symbolically. And for those of us who are familiar with Roman numerals, we know that the Roman numeral 3 is simply given by 3 vertical lines. So that would be now an example of a symbolic representation, because an analogical representation is an example of an analogical representation because there's a physical similarity between the two states of the system. That is to say that we have a 3-dashed insignia, and we have 3 items to which we are referring. Okay? So there's a physical correspondence in an analogical representation. Another example of an analogical representation, where the physical correspondence is very clear, is simply a map. You might have a map of this campus or a map of your hometown. That map is something you can typically hold in your hand or hold on your electronic device. And there's a correspondence between the layout of the items on that map and the layout out here in the real world. Because there's a physical correspondence, we would say that this is an analogical representation. So when we're talking about time estimation, we might be thinking about the importance of memory, and we might be thinking about how memories can be formed either symbolically or analogically. Okay, a couple of other terms that we would benefit by refreshing our memory, and that is, or these include such terms as agonist and antagonist. If we think back to Intro to Psych, we remember that we were introduced to these terms when we learned a little bit about biological psychology, and we were talking about neurotransmitters and how the neurotransmitters are allowing the neurons to communicate one with the next. We have one neuron and another neuron, and in between them we have a synapse, and in that synaptic area we might have the flow of some neurotransmitters. We have a presynaptic neuron, a postsynaptic neuron. We talked about the role of agonists and antagonists. We'll remind ourselves here that an agonist is some kind of chemical that increases the effective level of a neurotransmitter at the synapse. So when we talk about the effective level, we're not necessarily referring to the absolute amount of that neurotransmitter, but we're referring to the extent to which that neurotransmitter is effective at that junction. If I have some kind of an agonist, for example, a dopamine agonist, that would mean that I'm increasing the effective level of dopamine at that synapse. On the other hand, if I have an antagonist, I'm reducing the effective level of that neurotransmitter at the synapse. So these are some terms that you might recall from Intro to Psych, and as you'll see, we'll have some really nice manipulations, experimental manipulations, in the world of time estimation that give us some idea about the underlying psychopharmacology of time estimation. Okay, so before we get to the psychopharmacology, and most relevantly for this class, we'll be talking about psychophysics, we'll remind ourselves of something that many of us who have seen prior lectures already know. It's something called a psychometric function. We've got a psychological axis, our ordinate, or y-axis, and we have the plot of time on this x-axis. So it might be, for example, that in a particular experiment where you're asked to estimate time, you're given two choices on every trial. And we call this an example of a two-alternative forced choice task. And your choices might be something like this. Listen to a stimulus and report whether that stimulus is longer or shorter than a standard. So on a given trial, you might hear an auditory stimulus. It might be a beep. And you're asked to estimate whether that beep is longer or shorter than some standard. We'll go with a standard of 8 seconds throughout this presentation. Okay. So we might have now the actual duration of the stimulus on this axis, and we might take our 8-second standard, center it right here, and then talk about stimulus presentations that might be something like 1 or 2 or 3 seconds longer than that 8-second standard, or 1, 2, or 3 seconds briefer or shorter than that 8-second standard. And your job, again, is simply to report either that this particular stimulus was longer or shorter than the 8-second standard. Okay. As you might remember, we get these smoothly varying curves when we tend to measure this, whether we're measuring it in humans or in animals. And as we start out on this side of the axis, where we have stimuli that are physically briefer than the 8-second standard, it's very unlikely that we're going to report longer in the presence of such a brief stimulus. So on this axis, we're plotting the proportion of longer responses that our participant makes, and we're almost never getting those longer responses when we have really, really brief stimuli. But as we lengthen the duration of our stimulus, we get an increase in the proportion of longer responses, and we get these smoothly varying functions. We mentioned a little while ago that we can talk about the precision of a response, or the fineness of a response. And that corresponds to the slope of these so-called psychometric functions. As we get really, really steep slopes, we have evidence for very precise responding. If we have shallower slopes, we have less precise responding. Precision in this particular case is referencing just how fine a measure we can have on this x-axis, or how fine an interval, or small an interval, to get some kind of change in our behavioral axis. Okay? So we can think of the slope of any kind of a line or any kind of a function as something akin to the rise on the y-axis over the run. And in some cases, we get a relatively strong rise for a relatively small change along the x-axis. A relatively strong rise for a relatively small run. And when that's the case, we say that that system is very sensitive to the physical stimulation. Okay? So greater sensitivity would be given by steeper slopes. So I've mentioned in a prior lecture, we talk about this notion of a small child who is very sensitive to events. What we mean by that is that the child has a big change in behavior for a relatively small event. Same thing would go on here for psychometric functions. We have a relatively large change in behavior for a small change in physical stimulation, in this case the duration of a stimulus, and that would indicate that we have great sensitivity. So precision is given by slope. We can also talk about the accuracy, which we had defined earlier as the extent to which an observation matches some kind of a standard. Our standard in this experiment has been an 8-second stimulus. And we sometimes have briefer or longer stimuli. And we can see that these differently colored functions are sometimes to the left or to the right of dead center. So what we can do is measure something that we called in a previous lecture the point of subjective equality, or PSE, and go to the 50% mark on the y-axis. Up here we're always saying longer. Down here we're never saying longer. We're always saying briefer. At 0.5 we're equally likely to use those two possible response options. So that is a neutral point. That's the point at which we believe some stimulus is corresponding to the standard, in this case 8 seconds. So let's now start at 0.5. We'll march over until we get connection with the red line, and then we'll drop down, and we can see that that red line is centered exactly at 0. In this case, this person's point of subjective equality exactly matches the physical standard. This person has a neutral response bias. There's no bias here whatsoever. But left and right of that, we have different kinds of performance. If we start here at 0.5, march over, and drop down, we might see that this person who's represented in the blue curve has a bit of a mismatch. They believe that a stimulus that's 1 second short of 8 seconds is actually 8 seconds long. This is their point of subjective equality. So there's a mismatch between their estimate of what is 8 seconds long and what is actually 8 seconds long as given by the physical measurement on our x-axis. We can do the same thing with the curve shown on the right. You might be able to see that's a light green color. We start at 0.5, we march on over, we get to some intersection with the observed point, we drop down, and now maybe this person has a 1 second mismatch but in the opposite direction. So this person might believe that a 9-second interval is actually equal to the 8-second interval. So they're mismatching, even though all three of these participants have the same slope. They're differing from each other in accuracy. Some of the articles that we've read for the session supported by this PowerPoint slide are articles that pertain to how we estimate time when we're on marijuana, commonly known as pot, or when we're listening to music. And some really, really interesting phenomena occur when we're under this kind of stimulation or under that kind of stimulation. So let's take a look at how that is. Here in the blue, we have what would typically happen if somebody has been exposed to a THC agonist. And so THC, as you might know, is the active ingredient in marijuana. And what THC tends to do is it tends to have this effect. Physical time seems slow, as if your psychological clock is ticking faster. Okay? So sometimes people who are on marijuana will report that things are really dragging and everything's taking so long. Young children have a similar kind of response. Maybe they're excited about visiting their grandparents, and they're on their way to grandma's house or grandpa's house, and they're asking questions like, are we there yet? Are we there yet? To that young child, it seems like we should already be there. This is taking forever. When are we finally going to get there? The kid might say. Okay? This is the same kind of effect that we have on time estimation when we expose our participants to a THC agonist. This effectively increases the level of neurotransmitter inside of the system when we have any kind of an agonist. And these would be cannabinoid receptors. That would be the type of protein receptor that's going to be sensitive to THC, the active ingredient in marijuana. So we get essentially a leftward shift. Okay? Only 7 seconds perhaps have elapsed, but it feels subjectively like 8 seconds. Okay? So it feels like we'd have to ask ourselves the question, are we there yet? Are we there yet? It seems like we should be there. It seems like enough time has elapsed. This is exactly opposite to the kind of effect that we get when we listen to music. And whether it's positively valenced music, music that makes us happy, or negatively valenced music, music that makes us sad, some research has suggested that we tend to have the same kind of effect regardless of the valence of music, and that effect is the following. We tend to have music or a THC antagonist deriving physical time, or making us experience physical time, as if it's flying by. Time seems to fly when we're listening to music. So here we are on the x-axis. We can begin marching over, we begin going upward, and now, as we said a moment ago, we have a mismatch. Okay, so maybe actually 9 ticks on our physical clock have elapsed, but we experience that as if it were only 8. And then somebody tells us, you know, it was actually 9 seconds that elapsed, not 8, and we say, wow, time flies. Exactly the opposite of the experience that we have psychologically when we're on some kind of THC agonist and when we're smoking pot. Okay? So very different kinds of effects on time estimation when we're on pot versus listening to music. And it's not so much a shift in the slopes. These slopes are really quite comparable to each other. Rather, it's a change in the point of subjective equality, which corresponds to our accuracy, the extent to which our estimate of time matches a standard. Okay, let's see if we can say that same idea a different way. In this slide, we'll talk about understanding time estimation, but we'll do so by first referring to the middle of the slide, where we're going to pretend that this corresponds to the physical time. Okay? So we're talking about estimating an 8-second interval. And for those of us who know a little bit about music, these symbols correspond to eighth notes. I happen to have 8 of these here. And so we're going to pretend that each time we have a symbol, regardless of how it's notated, we have 1 tick on the physical clock. Okay? So we have a total of 8 ticks on our clock. That's our 8-second standard. We might ask then, how does our estimate of time change when we're listening to music or we're on some kind of THC antagonist versus when we're on a THC agonist, maybe when we're on pot. Okay? So we'll see how our time estimate changes. So here we are on the physical clock, and we're going to go up here when we're listening to music. What might happen when we're listening to music is something that is akin to having just 4 beats of time when the real clock has ticked a total of 8 times. And then somebody comes along and tells us, you know, 8 seconds have elapsed, and we would say, gee, it seems like only 4 seconds, time is really flying. So it's almost as if we get an alteration in the rate at which our internal clocks are ticking when we're listening to music. This kind of slowing of our internal clock, if I can call it that, we might call it a pacemaker. Okay? This kind of slowing would generate a rightward shift in the PSE, or point of subjective equality, as we see over here. Okay? A rightward shift relative to the neutral point. By contrast, we can drop all the way down here in this blue area, and if we have some kind of THC agonist inside of our body, where we're now increasing the effective level of that neurotransmitter at the cannabinoid receptors, increasing the effective level in between our 2 neurons at the synaptic junction, we might have a hastening of our clock. So now this clock is ticking away really, really quickly, as if we're anxious about something. And maybe in this physically 8-second interval, we now have a total of 16 ticks, okay, on our clock. And we use that number of ticks to estimate time, and we think a full 16 seconds have gone, and yet somehow we're told that only 8 seconds have elapsed. And we might be perplexed by that, and we might say, gee, it seems like this has been going on for a long time. Are we there yet? Okay? So we're getting very opposite kinds of effects. When we have the hastening of our internal clock, we're going to get some kind of a leftward shift in our point of subjective equality, as we see back over here. Okay? So leftward shift, rightward shift, opposite effects, listening to music versus being on some kind of THC agonist. Okay, so we'll talk now a little bit about 3 different theories of time estimation and 3 different ways of explaining the phenomenon in which the PSE might be shifting to your right or shifting to the left. Okay? One refers to the internal clock, and we've already said a little bit about that. Another refers to a memory bias that we'll come back to. We've already talked a little bit about symbolic and analogical representations. Another one is attention. So these 2 anyway, are very psychological, right? Psychological phenomena that might be affecting our time estimation. We can also talk about pharmacological influences. Just to give you a little preview of these different theories, we might talk again about this internal clock, a biological pacemaker that might speed or slow depending on the kind of experience that we're having with the environment. It might be a musical experience. It might be that we're becoming intoxicated with the active component of THC in marijuana. And we'll get PSE shifts that reflect the speeding or slowing of the internal clock. We'll see a couple more examples of those. We could have a memory bias that we could describe this way, that whenever we're making any kind of timing estimate, we have to take the number of paces that we have from our clock or number of pulses rather, that we have from our clock, and we compare that to some kind of memory estimate. Okay? And that memory estimate itself might be biased one way or the next. Those memory estimates presumably come from long-term memory, or LTM, and that might introduce an inaccuracy, a leftward shift or a rightward shift. Finally, we might have some kind of attentional bias. The pulses from the biological pacemaker, our internal clock, those might be accumulating, but maybe we miscount those because we're distracted in some way. And if we've miscounted the number of ticks that our biological clock has given us, then it might be the case that we have a misestimate in our time. So let's zoom in on some of these different ones, talking first about the internal clock. Here, we're going to refer to our internal clock within the context of something called an information processing diagram. In an information processing diagram, we typically have different boxes that correspond to different kinds of phenomena that collectively speak to, in this particular case, time estimation, but it could have been any other kind of psychological event, for example. Here we're going to have an internal clock that starts our process, and this is essentially emitting pulses. It's kind of like a pacemaker. You might think about this as the rhythms in your brain that might be measured by an EEG or electroencephalograph. Okay, we can measure things that way. There might be circadian rhythms. Our bodies have all kinds of rhythms, and we can count the number of pulses even implicitly. We might have some awareness of how many pulses have elapsed per unit time. These, according to this information processing scheme, land in some kind of an accumulator. It's a counter. This puts out the pulse, this counts the pulses. Okay? So we get an accumulation of pulses over time. Okay? And we might compare those accumulated pulses to some estimate that we have of how many pulses we would need in, say, an 8-second interval. We have long-term memories corresponding to how long a week is, how long a year is, how long 8 seconds might be. In this diamond-shaped box, we have a decision rule where we make a comparison between two inputs, an input that comes from the accumulator and an input that comes from our long-term memory of the interval that we're estimating. Again, maybe an 8-second interval. And it's a very simple decision rule. It goes like this. If the accumulator's value exceeds our long-term memory value for 8 seconds, then we'll say that that stimulus was longer than 8 seconds. And if not, we'll say it was shorter than 8 seconds. It's really quite a simple model. It has inputs from long-term memory and from the accumulator, which is simply counting the number of pulses that come from our internal clock. So what we might do is focus on this internal clock and ask questions about how can we psychopharmacologically manipulate the rate at which that clock ticks, and what kinds of changes do we therefore get here in our decision rule. So we're back to the slide that we had a little while ago. These are the psychometric functions, but now we're going to add just a little bit more detail. First, I hope you'll take note, on top of your PowerPoint presentation, you will see that way up top we have internal clocks and pharmacology, and we're going to make a pharmacological manipulation. Right beneath that big red lettering, we have finer black lettering that says dopaminergic compounds immediately modulate internal clock speed. So there's a lot of terminology there. Let's see if we can get to that. Dopaminergic compounds. So what we mean by this would be some kind of a compound or a chemical that affects the level of dopamine. Dopamine would be the neurotransmitter stated in noun form. If we turn that into adjective form, we get from dopamine to dopaminergic. That's typically the terminology that's used. Okay? Now, in this particular case, we have a dopamine agonist, and it's called methamphetamine in one particular case. And by the way, if you're looking at this electronically, you can click right on methamphetamine, and you can go out to a very interesting article by Warren Neck, who talks about using dopamine and a dopamine agonist while measuring time estimation. And we get the kinds of effects that we see in this slide. This administration, or administration of this kind of drug, tends to reduce the PSE, or the point of subjective equality, from maybe over here to now a -1 value. In the example that we've been developing, that would be a change in the PSE from 8 seconds down to 7 seconds. So it's almost as if our clock is speeding. Okay? We now have a faster ticking clock, rather than where it should be ticking at this kind of a speed. Okay? And so we are going to think that 8 seconds have elapsed actually sooner than they have. And so we're going to have this leftward shift in our PSE. Okay? And this comes about whenever we have a dopamine agonist, one example of which would be methamphetamine. Again, I encourage you to click on that and go out to the article by Warren Meck. That will be an abstract listed in PubMed. Now we can go to the other extreme, and this is really what I think is very interesting. The same researchers can do a different kind of manipulation, still using dopamine, still altering the dopamine levels, but now reducing the effective dopamine level at the synapses. This would be done through a dopamine antagonist that reduces the effective level of that neurotransmitter, dopamine. And that particular drug might be called haloperidol. Again, this is underlined in blue. Please click on that. Please go ahead and, if you need to stop the video, do that right now. Click on that, and you'll see that takes you right out to the abstract in PubMed by Warren Meck. And as you might know, haloperidol is an important drug in the world of abnormal psychology or clinical psychology when we're dealing with individuals who are suffering from schizophrenia and they're very symptomatic. If they're showing typical symptoms of schizophrenia, it's the case that we can give them haloperidol, we can lower their level of dopamine, and this tends to have the effect of remediating or at least reducing some of their symptoms. So this is something that you might remember from Intro to Psych when you talked about a common treatment for at least the typical symptoms of schizophrenia. Okay? If we now administer this to, say, rats, which is what Warren Meck had done, we can get a systematic shift in the psychometric function. This would be now a rightward shift. We get an increase in the PSE from this point to that point. It's essentially akin to a slowing of the clock. So instead of the clock ticking like this, the clock is ticking much more slowly, and it takes us longer to get up to, for example, 8 ticks. And we would report, while we're under the influence of this dopamine antagonist, such as haloperidol, we would report that, wow, time seems to be flying. So what's really nice about this is that we can show either a leftward shift or a rightward shift by experimentally manipulating whether we've got a dopamine agonist or a dopamine antagonist. Another very interesting feature about this is that this drug administration tends to have a relatively immediate effect. We get an almost immediate effect, maybe on the order of minutes or hours. Okay? We can show this leftward and rightward shift. And if you look very carefully at the details of that study, the authors are able to pinpoint that this dopaminergic compound is working at this level. It's working to alter the speed of the internal clock. And this is how we generate left and right shifts in time perception. Okay, there's another way of approaching this. There are other kinds of pharmacological manipulations, again conducted by Warren Meck and also by Russ Church from Brown University. And that's by manipulating the long-term memory. Okay? So remember that in order to reach a conclusion about whether a particular stimulus is longer or shorter, we have the comparison of two variables. It takes two to tango. Okay? We're going to be talking about the value in the accumulator and the value from long-term memory. And the comparison of those two will be determining whether we're going to say longer or shorter. So I like to think of it this way. Let's imagine that I have an 8-second interval, and I'm going to make this my 8-second interval. Okay? Here I've got my accumulator, and I might have 1, 2, 3, 4, 5, 6, 7, 8 ticks. And here I might say that I've got something like an 8-second interval. If I have a greater number of ticks, I would say longer. A briefer number of ticks, I would say shorter. So the rate at which this clock ticks is going to have a big influence on the decision that comes out of this stage, whether I say longer or shorter. But the same thing is true for how it is that I estimate an 8-second interval from long-term memory. I need to compare these accumulated pulses to something, and that something is typically an interval of time that we recall from long-term memory. Now, what's interesting about that is that it might be the case that our clock is ticking in a perfectly calibrated manner, but maybe our memory estimate, shown over here, is too high or too low. And that, too, can have an influence on whether we're going to say longer or shorter. So let's take a look at what Warren Meck and Russ Church had found when they made a psychopharmacological manipulation, but now they're trying to alter the memory component in time estimation, and they're going to have a pharmacological manipulation of that memory to try to introduce some kind of bias in the person's response. Okay? So way up top, we have cholinergic compounds gradually modulate time samples from long-term memory. So here's a new word for us, cholinergic. And cholinergic is the adjective form of acetylcholine, or refers to the neurotransmitter acetylcholine. And we might remember that neurotransmitter from Intro to Psych. It's one of the earliest neurotransmitters to be found. And when we talk about compounds that affect the levels of acetylcholine at the synapse, we're talking about a cholinergic manipulation. So once again, Warren Meck, and this time with his mentor from Brown University, Russ Church, engaged in some kinds of pharmacological manipulations, offering cholinergic compounds, and they can get left and rightward shifts of the psychometric function. But in the details of their experiment, they're actually now affecting the time samples from memory. That's going to be the left side in this comparison. Okay? They're actually lengthening or shortening the times that we remember from long-term, from our long-term recall. They're introducing skews in that estimate. Okay, so let's take a look at a particular case. If we look at acetylcholine agonists, and one particular one is shown here, physostigmine is how that's pronounced. It's kind of a fun pronunciation. Let's all say it together, physostigmine. Physostigmine was introduced into the animal system, and it tended to reduce the PSE, getting a leftward shift, by shortening the remembered time. Okay? So here our clock is ticking away. This is normally the 8-second interval that we'd be remembering. Here's our clock. Okay? But if we now have a shortening of the remembered time, then we're going to introduce a skew in our responses. This now 8-second interval is going to seem longer than maybe it should, according to our estimate from memory. And because it's seeming longer, we're going to be inclined to say longer. We're going to have a longer response bias, and that's going to shift the psychometric function leftward. Okay? Now, that's what happens if we have an acetylcholine agonist as our manipulation. Again, I would encourage you to click on that and go out to that article from Warren Meck and Russ Church. This was done when Warren Meck was, at that time, at Columbia University. Subsequently, Warren Meck moved to Duke University. Okay, another portion of that same study, and you can click on that over here, is to now do the opposite, that is to administer an acetylcholine antagonist. And that's called atropine in this particular case. And this tends to increase the PSE by lengthening the remembered time. So this hand I will always use to correspond to our long-term memory estimate. And here's our clock ticking away. Okay? That would be 8 seconds in each case. But let's say that what we're retrieving from long-term memory is skewed. Instead of it actually being an 8-second memory, we think it's an 8-second memory, but it maybe corresponds more to 10 seconds, for example. So now I've clicked away 8 times, but it doesn't feel like 8 seconds have elapsed yet. Okay? This would tend to move our psychometric function rightward. Okay? So we can now get leftward and rightward shifts by the administration of some kind of cholinergic compound. An interesting distinction between the cholinergic compound that we see here and the dopaminergic compound that we saw in the previous slides is that this cholinergic compound tended to operate more gradually. It took a longer period of time for this to have its effect than it did for the dopamine. And that might be because we can only alter long-term memory very, very slowly over a period of maybe many days, many weeks, and so forth. By contrast, we can alter the speed of the internal clock almost immediately, on the order of minutes or hours. Okay, so let's go to one last possibility. We'll talk about how we might be able to alter the response that we're going to make, represented here in this decision box, by looking at the connection between the internal clock and the accumulator. And this is going to be an attentional connection. This attentional connection is going to play a very important role, and we'll just remind ourselves of how it is that we define attention. Attention might be defined as the selection of an event. It might be the selection of a memory event. It might be the selection of a sensory event. But you might imagine that the clock is ticking away, and we are momentarily distracted. Okay? And if it is ticking away while we're momentarily distracted, we might miss or fail to select a few of the pulses. To the extent that that is true, we will wind up with maybe fewer pulses counted in our accumulator than we should have had, and this will create some kind of a misestimate in our decision rule. Okay, so there are different kinds of theories about how attention might be working. Theories about attention include the following. There's the attentional gate theory and the attentional flickering theory. In the attentional gate theory, we talk about some kind of a delay or latency in the time at which the participant selects or attends to the pulses. So it might be the case that we're asking our participant to estimate this 8-second interval, but for whatever reason, maybe the person is not tuned into the stimulus at its start. Okay? So they miss the first couple of pulses, and when there have been a total of 8 seconds that have elapsed out here in the real world, maybe they've only counted 6 of those 8 because they failed to attend to the early portion of the stimulus presentation. If that's the case, it might be that we have our 8-second interval here. They've only counted something like 6 seconds, so they're going to need 2 more pulses, okay, which would actually be a total of or totaling to the 9th and 10th pulse. Okay, so there's going to be a misestimate that we get because they didn't tune in at the right time. They didn't begin selecting at the right time. This will predict that the PSE will be the same absolute size regardless of the interval being timed. So if we're always missing 2 pulses because it takes us a moment or 2 to tune in, then whether we're estimating an 8-second interval or a 10-second interval or a 45-second interval, we will always be missing those 2 pulses. Okay? So this predicts then that we'll have the same absolute size in our mismatch regardless of the interval that we're estimating. A very different prediction comes from another attentional theory, one that we might call attentional flickering. Here, this theory poses that maybe we do tune in on time, but across the interval that we're estimating, we have our attention waxing and waning. And because the attention is waxing and waning, we miss some pulses. So we miss some pulses here, we miss some pulses here, and because we're missing pulses, we're going to be misestimating in each case. But what's interesting about this is that the attentional flickering theory predicts that the PSE shift will be proportional to the interval timed. So let's say that we're tuning in and selecting pulses only maybe 75% of the time. Well, it might turn out then that if we're estimating a 20-second interval, we will have counted 15, we'd be off by 5. But if we're estimating a 200-second interval, we will have counted only 150, we'll now be off by 50 rather than being off by 5. So we get an expansion or contraction of the number of missed pulses depending on the interval that we're estimating. So we get different kinds of predictions from the attentional gate latency theory versus the attentional flickering theory. So just to begin to wrap up, we have different kinds of theories about time estimation. We have theories that pertain to attention, but also theories that pertain to the memory component. We have theories that pertain to the rate at which the internal clock is manipulated. What's great is that in experimental psychology, we can directly manipulate the pharmacological state, we can directly manipulate the attentional load, and we can see systematic, reproducible shifts in the point of subjective equality, which tell us about how accurately or inaccurately we're estimating time. So I hope that you'll make some notes on your PowerPoint printout relating to any of the issues that we have had. I hope you'll think through some questions, and I hope that you'll bring those questions to class. See you in class.